Well, thank you very much for the invitation. Russ, I mean, we don't know each other well enough that I have any good story to tell you, so I drew to you a very lame birthday cake. It's lame for several reasons. I mean, this is due to, this is an approximation of the hexagonal lattice, as everybody can see. And you will notice that the cake is two-dimensional, which is very lame, right? But the point is that otherwise you would have told that I was part of the 90% of people who cannot do statistics, because the probability of this under my model would have been 0 with some. So this, at least I can tell you, this has positive probability for the model I'm going to describe. Okay, so as Stas said, I mean, it's difficult to make one elegant paper a year. And I do think that this year we did make an elegant paper, but we are 2 speakers here on this paper, so it will be actually Vincent who will describe it. So I'm going to do the old stuff, and I'm sorry for people who already saw it before. Still, I'm going to, I mean, maybe the 15 first minutes are kind of standard, but after that I'm going to try to describe new things that you can do with parafermionic observables. Okay, so the goal of this lecture is to tell you a little bit about the parafermionic observable for the loop ON model. So let me start by defining the loop ON model. So it was perfect because yesterday somebody did some simulation and showed some simulations. So thank you, Yinon. So the model is the following. You take the hexagonal lattice, and on this hexagonal you cut a part of it, a finite graph, which I will call a domain. So what is a domain? You just pick a self-avoiding polygon in the triangular lattice, and you just cut through this polygon. Inside it, you will have a finite piece of the hexagonal lattice, right? So the triangular lattice is a dual of the hexagonal lattice, so you will get a finite piece of the triangular lattice, which has the property that it's connected and its complement is connected. So that's what I call a domain. And from now on, domain, I will call them omega, and it will always be of this type. So there will be the boundary of omega is a polygon, a self-avoiding polygon on the dual of the hexagonal lattice. So now that you have your domain, what you do is inside this domain, you pick loop configuration. So it's just configuration of non-intersecting self-avoiding loops. Okay, let's call E omega empty set the set of these guys. Okay, you can also see them as even subgraphs of omega. Right? So this is the space of configurations. This is an example, maybe the best one. And from it now, you sample it at random according to a certain law, mu omega, which depends on 2 parameters, and which gives to a probability to a measure which is proportional to x to the number of edges in your configuration omega, and to the number of loops. So this is number of loops, and this is number of edges. And if I want to have a probability measure, I need to renormalize by a certain factor, the partition function, which I will denote like that. So there are 2 parameters, x and n. And the model now, you want to study the phase transition in this model. How does a large sample of this model look like? By the way, it was introduced by Nienhaus and his collaborators in the 80s, maybe 81, something like that. And it's kind of an approximation of the spin ON model, of the high temperature expansion of the spin ON model. But I mean, we should kind of sometimes ignore the motivation from physics and just look at it as a beautiful model that you want to study on your own. Okay, still, physicists are helpful. So there is a conjecture for this, this model that it undergoes a phase transition like that. So define L to be the length of the loop of 0. There may be no loop at 0. In this case, it's just like a trivial loop of length 0. Okay? And there is a conjecture that there exists a critical parameter, xc of n, which a priori is between 0 and infinity. such that for any x smaller than xc of n, there exists a constant such that basically the length of the loop at 0 decays exponentially fast. So mu omega of length larger than k is more than exponential of minus c times k. And this for every k. Also for any omega. You can take omega as big as you want. That won't change anything. And for any x larger than xc of n, well, in fact, in this case, if you look at the expectation of the length, it's infinite. So you don't have at all exponential decay. And in this case, in fact, maybe that's not exactly how Enon described it yesterday. So he had these two pictures, which were basically describing, you take a big domain, omega, say a box of size n. And there was a simulation of a typical loop configuration in this box. In this case, the biggest loop in the box is going to be logarithmic, right? In this case, in fact, you can really prove something stronger than this a priori, which is that they are really macroscopic loops, typically. Okay, so it's a dichotomy. In the case 1, you will have only small loops. In the case 2, you will have sometimes macroscopic loops. That's probably the most interesting case from the physics point of view, because it's a case where you expect conformal invariance and so on. So, I mean, I hope the story that we will remember together from our encounter will not be that I'm the lame guy who cannot handle conformal invariance, because after the two talks of this morning with, conformal mapping and things like that, here I'm definitely going to do everything without conformal invariance. I will not touch conformal invariance whatsoever. But indeed, if you think of it, this is in the regime in which you expect conformal invariance.
So what do you really mean by 2? The
Sorry?
omega is some finite domain.
Yeah, omega is some, okay, sorry. So, yeah. Omega now is not a finite domain anymore, it's H. So I didn't tell you how you can define it in infinite volume, and in fact, it's not at all clear. But this whole behavior is actually not at all clear. So this is a prediction. So the conjecture is this one. And the conjecture that goes even farther. Nienhuis predicted that, in fact, xc of n should be infinity if n is larger than 2, and should be 1 over square root of 2 plus square root of 2 minus n. Do not run, please. Okay, if n is smaller or equal to 2. So this is very special value. So in particular, there is a phase transition. There is something very different happening when n is larger than 2 and when n is smaller or equal to 2. That's the conjecture. Already this was unclear. This thing is even less clear, and with that, it becomes just science fiction, basically. Maybe not, I don't know. Okay, so how can you try to say anything non-trivial on this? Well, you need an advisor who introduces something useful. So we are going to introduce and work with what we call parafermionic observables. Okay, so what are these things? Well, in the case of the hexagonal lattice, they are fairly natural and simple to define. What you are going to do, you take a domain. This is your domain omega. And you pick a point on the boundary A. So what I mean by the boundary is that I will see my domain as really what you cut when you remove your self-avoiding polygon. So you have half edges like that, lying at the end of the thing. So I include these in my domain. So if I only look at loop configurations, of course, this doesn't change anything because you cannot have any loop going through these guys. But now what I'm going to do is I'm not going to look at loop configurations. I'm going to look at loop configuration plus a path from A to a mid-edge Z, to the middle of an edge. Okay, so you have in the middle here an edge, and you fix Z, and you look at now this type of configurations. Let's call them E omega AZ. And the parafermionic observable is going to be a function on my lattice, on my domain, sorry, that will be a function of Z, But if you think about it, there are a bunch of parameters which are associated to this function. And the definition of the function is that you are going to sum x to the number of edges in my box and to the number of loops, in my configuration, for omega in E omega AZ. So this will be just the partition function type thing. But I'm going to add here a winding term called e to the minus I sigma times the winding of this. So what is this thing? Well, you have a path from A to Z. Let's call it gamma. And this path does a certain number of left and right turns. So the winding here of the curve is pi over 3 times the number of left turns minus number of right turns. Okay? So now, I didn't tell you what sigma is, but now when you weight your configuration with one path, they don't always get only the weights. Sometimes they are twisted by a complex number that is going to depend on how many turns you do around Z before reaching Z. Okay? Okay, so that's the definition. It was introduced by Stas. In fact, in hidden ways or in different ways, it already appeared a little bit before. You can even go maybe back to Kadanoff, so in the maybe early 80s. But what Stas noticed, and really the important step here, is that this observable, was introduced for a reason. There is something special about it. And that is my number 3, which is it satisfies some form of discrete holomorphicity. So what do I mean by that? I mean that if you pick n smaller or equal to 2, and that already is something striking that the n equal to here does appear in the condition there. If x is equal to xc of n, exactly this guy, that's also very good news. And if sigma satisfies the following relation, that's not the elegant part of the talk. So this is, of course, what you would like to take for sigma, but whatever, pick that for sigma. Always trust your advisor. So if you do that, then P minus V f of P plus Q minus V f of Q plus R minus V f of R is equal to 0 when P, Q, and R are the following. You take a vertex inside your domain. So it's really a vertex of the hexagonal lattice. And you just index the 3 mid-edges, P, Q, and R, around it. Okay, you have 3 mid-edges. It's a vertex really inside. Then P minus V f of P plus Q minus V f of Q plus R minus V f of R is equal to 0 when you see P, Q, R, and V as complex numbers. So it's basically f of P plus J f of Q plus J squared f of R equals 0. So you have a local relation between the values of the observable around the 3 vertices, the 3 mid-edges. So up to now, I see like many bored faces. It's normal because this you already saw several times. Don't worry, in like 3 minutes we start to do things that are a little bit less classical. But I want it to be self-contained. And in particular, I'm not, I do not claim I'm going to be self-contained, but I wanted to have some introduction that could be understandable for, I hope, everybody. So here, I want to interpret that. This relation is exactly the same as doing the following. Doing a discrete contour. So you take this path, let's call it C. It's a contour on it's just a self-avoiding polygon on the triangular lattice. And there is a natural notion of integral along this contour, which is saying it's this minus this times the value of f here, plus this minus this times the value of f here, etc. This is just a restatement of the discrete contour here vanishes. So it's the integral around C of f of z dz equals 0. It just means that. But notice that since I chose a domain, any discrete contour can be written as a sum of these elementary triangular contours. So if I have this for these elementary triangular contours, I have it for every contour. So I get something which is a weak form. I mean, it's a discrete version of Morera theorem somehow. The discrete contour integrals for this function is 0. Okay, so now you have two ways of looking at that. You have the the pessimistic way, which is basically saying, well, okay, good for you. You have relations, but let's count the number of relations. Okay, you have one relation per vertex in your domain. How many unknown variables do you have if you want to determine f? Well, you have one value of f per edge. Okay, it's a linear system. It's very, very much underdetermined, right? So, okay, just drop it and go back to your studies. Well, not really, because maybe you can be optimistic and say, okay, maybe for special values of n, there is something happening. And there is indeed one value of n where something is happening is n equal 1. So for n equal 1, I'm not going to tell you really what happens, but these relations, they get strengthened. They are much more strong. Oh, much stronger, sorry. Anyway, you can extract really information from them exactly for this special value of n equal 1, and that's what Chelkak and Stas did. So in this case, in fact, you can even get conformal invariance simply because, I mean, simply is maybe not the right term, but because you can take the scaling limit of this thing. This function, if you renormalize it properly, you can take the scaling limit, meaning you take a domain, you take finer and finer mesh size, and you get from it the scaling, you identify the limit of f. And from that, you can get the full conformal invariance. So that's the work of Chelkak and Smirnov. And it's special to n equal 1 that there is this miracle that these relations that are a priori giving you a very undetermined system actually give you much more information and the complete information. It's really specific to n equal 1. Okay, n equal 1 is a very important case, in particular because that's the Ising model, but it's not the only case you would like to study. So what do you do when you don't have full information? And that's my title. There you need to squeeze some juice from something which a priori doesn't have any. A priori, you could really believe, okay, it's an underdetermined system. It doesn't give me much information. So the rest of the talk is to try to give you examples of how you can get information from that nonetheless. Okay. So I think the key observation there, if you want to be a little bit more optimistic and think that even for n not equal to 1, you can get information, the key information that the key idea you want to do is to basically do contour integrals on the boundary. So for any path, any domain, any contour C, you have 0 integral. Well, just do it on the boundary. Take C to be the boundary of your domain. So use that the integral around the boundary is 0. Okay? For every domain, it gives you one relation. Maybe it's a completely empty one, but a priori, you get a relation. And observe the following. So if I rewrite this, so let's take, so I have my domain like that. This is omega. And let's really go clockwise, I guess. Okay, let's go like that. And let's, for simplicity, because you can always assume that, let's really assume A is like that, right? I mean, it could be in different orientation. Let's assume it's like that. It's not going to be a loss of information. So how do I translate that? So first thing, what is the contribution of f of A? So if you are like that, the edge is going, the path is going like that when it crosses the thing. So there is a -1 due to the contribution of the P minus V, if you want. And then the observable at A, if I go back to the definition here, so it's the sum of every loop configuration. There is a path from A to A. What is the only path from A to A? Well, it's just the empty path. So I'm going to sum over, in fact, even subgraph, loop configurations. The winding term is going to be absent, so I just get what I defined as Z empty set omega, right? And then I have the sum for every Z on the boundary, but Z not equal to A. Okay, let's look at this type of people. What is f of z when you are on the boundary? So on the boundary, you still have these terms, but the winding term, an observation which is going to be key for us, is that the winding term is deterministic on the boundary. Any curve, any path from A to Z, where Z is on the boundary, has the same winding. So let's call it W of Z. It's something that doesn't depend on gamma anymore, and if it doesn't depend on gamma, I can just remove it from the sum. So I get a term like that. Now, this guy is really not associated to any curve. You can compute it easily. And notice that the P minus V, in fact, if you think about it, it's just e to the I W of Z. It's the same thing when you compare it to P minus to the A minus Z. So overall, when you sum the thing, you get the following relation. You get that this plus this is equal to 0, where this is the partition function on any loop configuration with a path from A to Z. But the important thing here is that there is no winding term anymore in this partition function. Okay? So let's maybe rewrite it like that. This is equal to this. Okay, that is really the observation I want to make. Sorry, yeah, there is a question? No? Okay, sorry. So you have a relation for every omega. Now, let's pick a very special omega, okay? I mean, a very special type of omega. I'm going to make a further assumption on omega, which is that, so you have A like that. I'm going to assume that here there is an opening of k pi over 3. And two lines really going to something that looks like that. So I take a very special type of omega. Okay? So think, for instance, for k equals 3, it's going to be a subset like that. You take a domain like that, and you look at something. It's a special type of omega. And what I claim in this case is that Z empty set omega is equal to the sum. Here you could also take the real part if you want. Do you want? Yeah, maybe I want. Okay, take the real part. So this is cos of 1 minus sigma winding. So the observation when I do something like that is that all the terms on this part, all the terms that are close to A, they receive the same winding. Right? Which is what? It's k, I mean, let's maybe look only k is this thing. It's k pi over 3. The winding of these terms. Right? In this case, anybody here gets a winding pi, and everybody here gets a winding minus pi. So if you take the cos, you don't see any difference, and you get the cos.
Why is the AZ real?
Sorry?
Instead of AZ of omega, why is that real? There's no winding.
Z of AZ omega is just the sum. Yeah, it's without this term. So it's just a partition. Yeah. Sorry about that. It was probably not clear. So here, you get 1 minus sigma, k pi over 3, times here the sum of the Z, A, Z, omega for Z on, let's call it omega 1 of omega. It's the first part of the boundary. And then you get a term. This one, I don't really want to touch it, on the end of the boundary. I mean, on the other part of the boundary. And from now on, I just want to tell you a little bit about this relation. Okay? So you get this relation for any omega of this type, you get a relation like that. And here you see clearly that there is going to be 3 possible behavior there. The first one is maybe this term, is equal to 0. Okay? This is either equal to 0, or maybe it's positive, or maybe it's negative. And my goal in the remainder of the talk is to give you an example of application for each one of these cases. Because here, I mean, you already saw probably the proof for safe avoiding walk, but I want just to put this into perspective and tell you a little bit what is the motivation and the intuition behind it. So you have this type of relation. This is either 0, positive, or negative, and let me give you 3 applications of that. Okay, so let's start by the simple case. Let's start, so this is 5, the case where the cos is 0. Or let's, case. Okay, so let me actually give you 2 applications, and there is one which I love very much. I think it's a very cute one. Take n equal 1. And take just the strip. Ignore the problem on the boundary, just take that. So in this case, so n equal 1, when you compute your sigma, you get sigma equal 1/2. Here k, okay, sorry, so k was the total opening, sorry about that. So k is equal to pi. So here I get cos of pi over 2. So I'm indeed in the case where I get, k equals 3, sorry. And therefore, I'm in the case indeed equals 0. So what do I get? I get z omega, z of the strip, empty set, is equal to the sum of a point z on the top of what is the winding on the top. But the winding on the top is 0. Right? You have no winding when you arrive at the top, so this term is just 1. And you get sum of the z, az on the strip. Divide by this. And this, in fact, for n equal 1, in something very classical, the high temperature expansion of the Ising model is the loop ON model with n equal 1. So this quantity is just a spin-spin correlation, in fact, in the Ising model. So here you get a funny relation, which is 1 is equal to the sum for for z on the top of sigma A, sigma z at criticality, at Tc. But now it's not a very big leap of faith. Actually, it's not a leap of faith at all. You can prove it, that all these terms are basically of the same order, or at least for the z that are close to. So what does it tell you? It tells you that the spin-spin correlation for the Ising model decay like 1 over t, 1 over the distance. So spin-spin correlation on the boundary decay like 1 over the distance. And here you don't need to refer to any conformal invariance for that. You don't need to refer to anything. You get it directly in a one-line argument from that. So this at least, I don't know whether it corresponds to elegance for many of you, but this I consider is an elegant part. So if it's not elegant, I will improve for the 70th birthday and try to do something better. But okay, so this is basically t times the correlation, let's say, of ti, like sigma 0, sigma ti. That's one application. Of course, you can get this result in many other ways. I'm not claiming this, but I do think probably that's the simplest way. Or no, the shortest way. Okay, let's do another example. Take n equals 0, okay? And take the following domain. So take a domain that looks like that, say. Okay? So what you do is you do an angle here of 5 pi over 3. So k is equal to 5 in this case. And sigma in this case is 5 over 8. Okay, you can compute with the value there. So it's 5 over 8. So again, I get cos of 3 over 8 times 5, sorry, what did I do? Well, but you do something. This is, again, the case where the thing is equal to 0. But that tells you something very interesting here, because it tells you that the value of the sum of these guys here is equal, well, what is the partition function for n equals 0? You have no loops. So the partition function is just the empty configuration, so it's 1. So it tells you that 1 is equal to the sum of the E on this domain omega, AZ, for every Z on the boundary, the far boundary, what is away from the thing. But this is what? This is just a number, is a partition function for self-avoiding walk from A to Z in this domain. So it's definitely smaller than the partition function of the generating function, sorry, of walks from A to Z in the full plane. There are more walks in the full plane. Well, sum over the distances now. This was, say, a box of size t, and you cut it like that. Sum over t. What do you get? You are summing 1, so you get something which is infinite. Right? So infinity is equal to the sum of the generating function for walks and going from A to any point. So it's just the generating function for the self-avoiding walks themselves. So infinity.
To avoid the angle, right?
Sorry?
It's not to avoid this.
Yeah, but this is actually worse for you, right? So if it's smaller than the generating function. Yeah. So what you get is that the generating function of the self-avoiding walk, when you apply it at xc, you get infinity. So what does it give you? It gives you that xc is actually larger or equal to 1 over 1 over mu, the correlation. Okay? So it gives you, this is a proof of the, I guess, lower bound for the connective constant of the hexagonal lattice. We didn't do it that way in the paper, but I think this is actually a nice way of doing it as well. So lower bound, so it gives you this, gives you mu of the hexagonal lattice is larger or equal to square root of 2 plus square root of 2. Let me just, as a parenthesis, because we have a little bit of time before I go back to actually things that are proved, give you one small observation on that which I find very cute. So imagine you are unlucky and you never heard about the SLE. So SLE was, never existed. You cannot use it. Can you predict any non-trivial exponent for the self-avoiding walk? It's not very easy. You don't have any exact computations or things like that. But here you have something interesting, because this tells you that this term is typically of order 1 over the distance. Right? If this is t, this term here, so the generating function is typically of order 1 over t. They are typically all of the same order, which is actually true. So here it's numerology. I'm not proving anything. And again, it's a parenthesis. If you don't like it, you can just start snapping for like 2 minutes. So this tells you that. But now this term, think percolation-wise, this term should be kind of the cost of having like a self-avoiding walk like that times the cost of having a self-avoiding walk like that. So imagine, let's define Bt to be the partition function on any walks from 0 as a generating function. We will not manage to get it. Generating function for any walk from 0 to height t, which stay in this strip. Okay? So when you look at this guy, here what you pay is, you can imagine that you pay 1 over t to the alpha to stay in the strip there, and 1 over t to the alpha to stay in the strip there. Okay, now let's look at this term. Or like say the sum of these terms. Well, these guys, you should pay 1 over t to the alpha to actually stay in this strip there, right? I mean, here you are trying to get close to a flat angle, so it should cost you 1 over t to the alpha. Really think percolation-wise. And in the second case, here, you need to pay the cost of staying in this wedge. So it costs you 1 over t to the beta with beta another angle. But okay, you don't know SLE, but imagine you still know conformal invariance. Like you heard about this thing in physics about conformal invariance. If the cost of staying in a half plane is 1 over t to the alpha, the cost of staying in this image by power of one of the plane is going to be actually 1 over t to the alpha times 3/5, because the mapping between the two is z to the 5/3. Okay, but that means, and I forgot, that means that this should be, I forgot the 1 over t somewhere, but why? Sorry, it was from point to point. So I have t guys here, so I get an additional t, sorry. So you have order t people on the boundary. So you get this, and this I told you is of order 1, so it gives you that the alpha should be of order 5 over 8. So it gives you a non-trivial prediction for a non-trivial exponent in the self-forwarding walk model. You can actually extend that to other contexts. And by the way, this, if you massage a little bit more this relation, I'm not going to do it. You can even predict that the probability is that two self-forwarding bridges like that, so two self-forwarding walk going to height t, the probability that they intersect should be 1 over t to the 3/4. Actually, from this, you get it almost immediately. And it's basically a rigorous result from that to get to the other one. So you can really get some non-trivial information, even on critical exponents, which may look weird at first sight, because, again, you are only working with a very undetermined system. Okay, so that was the case where it's equal to 0. Let's look now at the case where it's negative. Actually, the fact that it will be equal to 0 is fine for us. So in the case where it's negative, what do you get? Well, you get immediately that this guy is larger or equal to 1. So it's typically something that is going to give you lower bounds on this type of quantity. And there is a special case where it's interesting to do it, is for n larger or equal to 1, n in 1, 2. So when you look at n in this regime, you can do the following. You can take this domain, like that. So again, it's an angle of k, it's k equals 3. And for n in between 1 and 2, sigma is smaller, is larger or smaller or equal to 1/2. It's equal to 1/2 for n equal 1, and it becomes smaller for n actually larger or equal to 1. So we are indeed in the case where this term is negative. Okay, so what does it tell you? It tells you that the sum over all, so the z empty, let's say in this triangle, is always smaller or equal to the sum for every z on the boundary of omega, so there or there. The cos is something which is going to be deterministic. It's going to be just a constant. Let's ignore it, or let's put a constant here. And you get the z omega, z triangle, sorry, az. So this kind of tells you, if you renormalize, if you put like that, I really hope they are not going to enter, because there seem to be many of them. Okay.
What happens to the other boundary?
Sorry? Just by symmetry, it's the same contribution. So I just included it. But otherwise, here, actually, it's really on both sides if you want. It's fine. But
why is the cost the same? The cost is different.
the winding is going to be minus the winding. So here, it's going to be pi over 3, and here, minus pi over 3. So it's really, they are related by just a minus sign, and therefore the cost is going to give you 1. So you get this. And from this, actually, if you massage the thing a little bit, you can manage to create loops. So this tells you that the probability of having some kind of probability, because that cannot really be interpreted as a probability, but it kind of tells you having long path in your configuration is not that costly. And from that, you can actually prove the following. You can prove that the probability in a big box like that, the probability of having a large loop the probability of having a large loop, in fact, using exactly that this thing is decaying no faster than 1 over t, here you can get that this thing is not decaying exponentially fast. So here there is some work. And actually that's a very elegant part of the argument, but I mean I was only asked to do one elegant talk, so just so here there is some work to be done, actually a lot of work. But you can prove that, and from that you can actually bootstrap it to say that it doesn't decay at all. So all of this to tell you that from this relation, with a lot of work, you can get this result, which is due to Yin and Spinka. I have always hard time with alphabetic ordering. Okay. Yeah, really. Okay. At least if I have hard time, I should do like that. That's at least a polite thing to do. So, which is going to tell you that at xc, you are actually in the regime where you don't have exponential decay of the length of loops, and you have actually big loops with positive probability. So in some sense, it's kind of one inequality in an in-house conjecture for the critical points. It's kind of telling you at xc of n, you are already in the critical regime. So n between 1 and 2, and x equal xc of n, you have big loops. That's one application. So overall, the only thing I want you to remember is you get lower bounds, but these lower bounds, they are actually, you can bootstrap by probabilistic argument to give you exactly the type of bound you want, the type of observable you want. I should mention very quickly, and then I go back to the safe-forwarding work because that's something that people like usually. Another application which has nothing to do is for the FK model. So I don't want to discuss anything there, except that using exactly this idea, there you can also define, so for the random cluster model, you can also define an observable. You can also do the discrete holomorphicity, and you can also find domains for which you are going to have an inequality of this type. And that was exactly what was used to prove that the random cluster model has a continuous phase transition for any q smaller or equal to 4. Why do I want to tell you that? Not because I want to advertise another result. It's just because there is an idea there, which I love very much, and I hope it's going to be useful in other domains, is that in order to get this coefficient here, I mean, in order to be in this case of smaller or equal to 0, in fact, you need to take k, which is larger than 6. That means you need to work with domains that do not embed properly in the plane. They are actually part of the universal cover of your domain. So there is something about studying this model on this kind of universal covers, which is, I think, a very nice, very nice problem. Okay. So that was just k larger than 6 sometimes. Okay, let's look at the last case, which is when it's larger or equal to 0. And the main application of that is going to be a simple application. Take n equals 0 and take the strip like that. So for n equals 0 and the strip, you can check that you are indeed in this case. And then that tells you that, well, here you would get that this thing was larger or equal to the contribution on these guys. Here, you are going to get exactly the opposite, right? The partition, the generating function on guys from 0 to the top, which I called actually BT earlier, BT has to be smaller or equal to 1 now, not larger or equal to 1. Okay? But that tells you something nice, which is that there is a classical argument on safe-forwarding work, very, very classical, that tells you that the generating function for the safe-forwarding work is always smaller or equal to 1 over x times the exponential of the partition function for the bridges. There are some factors, but the bridges is what? So b of x is just going to be the sum of the bt of x. So you don't take x equal xc, it's true for any x. And you have a bound between the number, the genetic function for self-forwarding walks and the generating function for bridges. Okay, but if you have bt smaller or equal to 1, so it's bt of xc smaller or equal to 1, then you get that bt of x is smaller or equal to x over xc to the t, simply because any walk, any bridge going from 0 to the top of your strip has length at least t. So for any x smaller than, and this is for any x smaller than xc. But that tells you that b of x is finite for any x smaller than xc. And that implies automatically that g of x is finite for any x smaller than xc. So g of x finite for any x smaller than xc. And that implies immediately that xc is larger or equal to, smaller or equal, I guess. No, larger, okay. So it's the other inequality. It gives you an upper bound on u. So basically, up to this identity, which I didn't prove to you, but which is go back basically to the first paper on self-forwarding walk, and conditionally also on the proof of this relation, this local relation, but which is very simple, you have a full proof of connective constant of the hexagonal lattice equals square root of 2 plus square root of 2. Let me finish by a conjecture. Something which I think, I would love to see a proof to that. I still have 5 minutes, right? No, I don't. I didn't start late. I even starting late, I already should be. No, that's, okay. State the conjecture? Okay. So just, if you look at the number of walks of length n, there is classical bound that it's larger than mu to the n and smaller than mu to the n times e to the square root n. And this e to the square root n just follows from this bound here. You can improve that in the case of the hexagonal lattice. It's an upcoming paper that you can do n to the gamma here, where gamma is smaller than 1/2. But the truth is actually much, much better than that. It should be here n to some power, which is 11 over 32, whatever, but n to some power. So I claim that via the self-forwarding walk, like parafermionic observable and so on, a sufficient thing to prove that is to prove the following claim. Pick a box of size k in your lattice and just remove it. Okay? Take the universal cover. Take the universal cover. Then there is a certain growth rate for the number of self-forwarding walk on this universal cover. Well, prove, so conjecture, there exists a k such that this mu c of k is equal to mu of the hexagonal lattice. If you can prove that, so it's decent to believe that this could happen, right? Because the only way it would not be equal to the connective constant of the lattice would be if the walks, it's actually very good for your walks to stick to the singularity and start winding around it and go ballistically in the vertical direction. That's not the vertical one, but anyway, in that way. But at the same time, conformal invariance and so on kind of tell you that it should not be the case. Yes?
What's mu of k?
So mu of k is the rate of growth in this universal cover. K is the size of the box that you removed. Yes. Sorry? I do believe it holds for any k, but it's a harder conjecture, a stronger one. But prove it for any k, then you can bound here, I think, by n to the 8 or something like that, using the parafermionic observable.
So, sorry, it's confusing. K is the size of
the box.
Box which you remove, and then
Yes.
you count walks of arbitrary length.
You really look at the rate of growth of walks, maybe up to translation, because here it's kind of less clear what you mean by that. But yeah, or let's say walks starting there. Look at walks of length n. Let n go to infinity. You have a certain rate of growth. You call it mu of k. Prove that for 1k, it's equal to square root of 2 plus square root of 2. And actually, it's very simple to prove that mu of k goes to mu of the hexagonal lattice when k tends to infinity. Prove that, in fact, it's true for, it's stationary. gets to the value at a finite k. If you prove that, then we can work together, and I give you this. Okay? Well, thank you very much.